Hello and welcome back. Today we will solve some more past paper questions from the topic photoelectric effect. And what I want you to understand is that if you pick any random question from past papers from this topic photoelectric effect, you will see that there is a pattern. There is a limited number of concepts that they test you on. So if you learn all these concepts, you can answer any question from this topic. And the number of concepts is actually very small. So these are all the concepts that you need to answer any question on photoelectric effect. There can also be, of course, a descriptive question, but we have already covered that in my previous video. So in this video, we will cover these concepts. And for graphs, I'll have to make a separate video. So all I need is just 5 minutes to explain the concepts. And at the end of 5 minutes, you will see that you will be able to solve these questions very easily. I can promise you that. So let's start. Let's start with the photoelectric effect equation. Okay, we know that HF equals kinetic energy plus work function. Now, to gain a deeper understanding of this equation, I want you to give this equation a different name. Can we call this equation, for example, an equation of motion? The answer is no. Can we call this equation conservation of momentum? The answer is no. Can we call this equation conservation of energy? And the answer is yes. So all this equation is just conservation of energy, right? We start with some initial energy of photon HF, and the electron absorbs this energy, uses some of it to break free from the metal surface, which we call work function, and the rest of the energy is used as kinetic energy of the electron. So this is what is happening. Electron is inside the metal surface. We have a photon coming in, which has energy HF. The electron will absorb this photon, will use some of the energy of the photon as work function, and the rest will appear as kinetic energy of the electron. So this is just conservation of energy, right? This is the first equation we need, and we also need to understand this equation to answer these questions. The second equation is just a review of that equation. I've already explained it in my previous videos. We just need momentum, P equals mv, and we need a definition of de Broglie wavelength, which is given by h over momentum. So if a particle has some momentum p, there is a wavelength associated with that particle given by lambda. Lambda will be the wavelength of the wave associated with a particle having momentum p. And what is p? P is just mass times velocity, and h is Planck's constant. So these three equations are very basic, and I think everyone knows about these equations. But this fourth one, stopping potential, is a bit tricky to understand, and the reason is that the theory that goes into stopping potential is taught in A2, but the questions are asked in AS physics. That's why most of the students struggle to understand this concept of stopping potential. But it's not very difficult to understand. It's very simple. Imagine you have two plates. This one is negatively charged, this one is positively charged, and I release an electron here. So I release it from rest. It has zero kinetic energy. What will happen? That this electron will start moving towards this positive plate, right? Because it's moving, it is actually accelerating, and just before hitting this positive plate, this electron will have some kinetic energy because of its motion, because of its velocity, right? Now my question is, where did this kinetic energy come from? We know that energy can neither be created nor be destroyed. Here, the electron was at rest. It had zero kinetic energy. Here, on the other side, just before hitting the positive plate, the electron has some kinetic energy. Where did this kinetic energy come from? And the answer is that although initially the electron had zero kinetic energy, but it had some potential energy, right? The total energy of the electron was not zero, just the kinetic energy was zero. Now the next question is, okay, what is the potential energy of an electron that is just sitting here? And to answer this question, we have to find the voltage difference, the potential difference between these two plates. Let's say the potential difference is just 1 volt. So the equation for potential energy of a charged particle in some potential V is given by potential energy equals charge on this particle, let's call it Q, times the potential difference between these two plates. Let's call it V because it's just 1 volt, so it's just 1 V. So what is charge on this particle? Because this is an electron, the charge is just E, which is electronic charge times the voltage. So it's just EV. This is the potential energy that the electron has at this point initially. And now if I ask you what is the kinetic energy of electron just before hitting this positive plate, we know that energy can neither be created nor be destroyed. So it means that all of this potential energy must have converted into kinetic energy. So it means that kinetic energy just before hitting this plate must also be E times V. Now, why do we need all of this for photoelectric effect experiment? And the answer is that in photoelectric effect, the exact same thing happens, but in the opposite direction. So the electron actually is going from this side to the other side, and we are trying to stop it from reaching this point. We are not accelerating it, we are trying to stop it. And just to remind you the connection and to give you the reference, we have this equation, photoelectric effect equation, in which we have kinetic energy of the moving electron. The question is, how can we measure this kinetic energy? And to measure this kinetic energy, we use the concept of stopping potential. Why do we call it stopping potential? The answer is what I explained here. The electron is moving towards this plate, and we are stopping this electron by applying some potential. So let's draw the same diagram, this time for photoelectric effect experiment. So electron is just emitted here. It is moving with some kinetic energy towards this plate. And when the electron reaches this plate, how will we know that the electron has reached this plate? We know this by looking at the current in this meter, ammeter, and here we can also apply some voltage. So the electrons are hitting this plate and we see some current here. Now we want to stop this electron from reaching this plate, which means we have to somehow oppose, or we have to somehow cancel the kinetic energy that this electron has. We have to counteract this kinetic energy, right? How can we make this energy disappear? By applying potential energy, like I just explained. How can we apply potential energy? By providing some potential difference between these plates. Now, in which direction should we apply the potential? And the answer is the potential should be applied in the opposite direction, which means we want this plate to be positively charged and this one to be negatively charged, so that this plate can attract this electron towards itself, which will stop this electron from reaching this plate. So that's why this potential, whatever potential you apply here, will be called stopping potential. So in summary, we increase this voltage by increments, and we look at the current meter and the current starts decreasing. We increase the voltage again, and we keep increasing it until we see zero current in the current meter, which means that now at this point, none of the electrons are reaching this plate, which means all the electrons are being stopped, which means that the electron with the highest kinetic energy is now stopped from reaching this plate. Now, how can we measure this maximum kinetic energy? And the answer is just by comparing the kinetic energy by the potential energy that was used to stop it. So potential energy that was used is just E times whatever the potential difference we have applied, V, and we set it equal to kinetic energy. So if this much energy was used to stop this electron from reaching this plate, it means that all of this kinetic energy must have been balanced by this potential energy. So that's why these must be equal, right? So 1/2 mv square, which is the kinetic energy of the electron, must be equal to the stopping potential energy. This potential is called the stopping potential, but if you multiply it with the charge of the electron, then it's called stopping potential energy. Okay, this is not just stopping potential, now it is stopping potential energy. This equation can also be used to find the highest velocity of the electron in photoelectric effect experiment. So you can just rearrange this equation for velocity and you will get an equation for the maximum velocity of an electron. So that's everything that you need to understand to answer these questions. Let's see. So the first question is, briefly explain what you understand by each of these terms in the equation. So we know that this is the whole equation is conservation of energy. So it means each term must be some energy. HF is the energy of photon. Kinetic energy max is the kinetic energy of the electron because of its motion or velocity. And this phi is called work function, which is the energy required for an electron to break free from the metal surface. The second question is, calculate the momentum of an electron traveling in vacuum at 5% of the speed of light. So first of all, we look at the equation for momentum that I explained, P equals mv. What is v? V is 5% of the speed of light, so 0.05 times the speed of light, 3 times 10 to the 8. This is the velocity. You just multiply it with mass of an electron and you will get momentum of the electron. Remember, always write units of momentum. So the units will be kilograms meter per second, and whatever the number that you get by multiplying mass of the electron and this velocity. The next question is, what is the de Broglie wavelength of electrons traveling at this speed? This is also, I just explained, if a particle has some momentum, there will be a wavelength associated with that particle, and the wavelength of that wave will be given by lambda equals Planck's constant divided by momentum. So you just need to divide the momentum that you just calculated from the first part, and you need to divide it by Planck's constant, which is just a constant, and you will get your answer A for lambda. And again, the units will be some units of length. Let's just call it meters. The next question is, why are electrons of this wavelength useful for studying the structure of molecules? Now, we have talked about this concept in detail in the topic of refraction and diffraction, but I will briefly discuss it here. So if you have a molecule made up of different atoms and you want to study the structure of this molecule, then the wavelength that you're using, the wavelength of that light must be comparable to the distance between these atoms. And you will see that the wavelength that you get from this part will be comparable to the distance between atoms in a molecule. So because this is of the same length, that's why this wavelength can be used to study structure of molecules. Basically, we need diffraction, and for diffraction, the wavelength of the light that we are using must be comparable to the distance between slits, or the slit separation. We have discussed this thing in detail in double slit experiment and diffraction. You can watch previous videos. In the next question, we are given a photoelectric effect experiment, and it is given that incident radiation has a wavelength of 215 millimeters. The metal surface of the photocathode has a work function of 2.26 electron volts. The first question is, calculate the energy in electron volts of a photon of the incident radiation. So we know that energy of the photon is hf, but to find the energy of photon, we need frequency. But in this question, we are given wavelength, right? So we need some other equation to find frequency from wavelength, and the equation is V equals F lambda. And if we want to find frequency, we can rearrange this equation for frequency, and also we need to change this velocity because we are dealing with radiation here. So this is not just any velocity, this is the velocity of light, which we call c. So c equals F lambda, and F should be c divided by lambda. Now what you have to be careful with this is that if you just substitute this frequency by dividing speed of light, which is 3 times 10 to the 8, by the wavelength, which is given here in the question, the frequency that you will get, you have to multiply with Planck's constant, and the answer that you will get will be in joules. But the question asked us to find energy in electron volts. So we need to convert joules into electron volts. First of all, we need a relation between electron volts and joules. So 1 electron volt equals 1.6 times 10 to the negative 19 joules. Now we need to make two conversion factors. So 1 electron volt divided by 1.6 times 10 to the negative 19 joules. This will be our first conversion factor. Or we can also write 1.6 times 10 to the negative 19 joules divided by 1 electron volt. Now let's say if you get some energy for photon, which will be hf, and you get some answer which is in joules. Which of these conversion factors do we have to use here to go from joules to electron volts? And the answer is that you need to multiply something with joules so that the joules in the denominator cancel with the joules here, and the electron volt in the numerator gets carried as the final unit in the final answer. So just by looking at these two conversion factors, we know that we have to use this conversion factor because it has joules in the denominator, which we need to cancel, and it has electron volts in the numerator, which we need as our final answer. So whatever energy you get from here in joules, you just multiply it with this conversion factor, 1 electron volt divided by 1.6 times 10 to the negative 19 joules, and you will see that joules will cancel with joules here, and you just need to divide the answer by 1.6 times 10 to the negative 19, and the final unit will be electron volt. And if you do all of these steps, your answer should be 5.78 electron volts. So I'm sorry, but I had to explain this conversion business in detail because I've seen so many students, they will get an answer in joules, and then they will be thinking like, do we have to multiply by 1.6 or do we have to divide by 1.6? And most of the time under pressure in exam, they, instead of dividing it, they just multiply it, or sometimes instead of multiplying, they divide it without thinking what they are doing. So make sure you have a very clear understanding of why you are multiplying or dividing by a certain number. It is actually this thing that you want to cancel one unit and you want to keep the other one, right? So depending on which one you want to cancel and which one you want to keep, you have to decide which conversion factor do you have to use. The next question is, what is the maximum kinetic energy in electron volts of the emitted electrons? So if you look at this question gives you some voltage here, but be very careful because you can also use simply conservation of energy to find maximum kinetic energy, right? So you start with the energy of photon, which is 5.78. This is the energy of photon, HF. And this energy is used as kinetic energy of the electron, plus some of this is used as work function, which is already given in the statement, right? It's 2.26 electron volts. So this is in electron volts, 2.26. This is also in electron volts. So to find kinetic energy, you can simply rearrange this equation, and because of conservation of energy, you should get the right answer for kinetic energy. So just subtract 2.26 from 5.78 and the answer will be 3.52 electron volts. And now the last part, write down the value of stopping potential that was used. Now you have to be careful here because in this question, you see this is a variable DC supply which can supply from -6 volts all the way to +6 volts. So this is the range of this variable DC supply, but we don't know the exact value of the voltage that we are applying here. So for this question, what we can do is we can set the potential energy EV, which was used to stop the electron, right? So the electron having the maximum kinetic energy was stopped by providing this potential energy by creating a stopping potential V. So this V is the stopping potential. If you multiply it with charge on an electron, you make it potential energy, and this potential energy was used to stop the electron having this maximum kinetic energy, which is 3.52 electron volts. So now the question is, what is this stopping potential? And the answer is, to find V, you just need to divide both sides by electronic charge E. So the E's will cancel and you will get V as 3.52 volts. Okay, so you have to understand that this 3.52 is different from this 3.52 because this is electron volts, which is a unit of energy, and this 3.52 is just volts, which is a unit of potential difference.